Good morning, guys. Yesterday we got cut off, but we were doing on your own 13.3. So I'm going to continue to finish that question. So let's jump in there. We were on step 3 of our problem, which was our Lewis structures. And I think I had drawn the first one, but I'm just going to start over and draw them all here together so you can see them. So first, we have our chemical equation. Here, I'll go ahead and type it here just so you can have a visual. So it was 2C2H2 plus 5O2. And that was going to make 2H2O plus 4CO2. That's our equation. So I'm just going to draw all of that in Lewis structures underneath. Okay, so first we have 2 carbons bonded together, which have 4 valence electrons each. And we have 1 hydrogen on each side. So we have 4, 8, 9, 10 to work with. That's 2, 4, 6, 8, 10. Okay? And there are 2 of these. So let's draw one more. Okay, next is going to be fun. We have 5 O2 molecules. So oxygen has 6 valence electrons. So O2, we would have 12 to work with. So that's 2, 4, 6, 8, 10, 12. Okay. I'm not going to draw the valence, the lone pairs here on the other ones, just because it's going to save us time. You know they're there. Mainly what we need the Lewis structures for is to count the bonds. So the lone pairs aren't going to matter in our equation anyway. So this is just going to save us time. Okay. So there's 5 of those. 1, 2, 3, 4, 5. Okay. And that is all going to make 2 H2O molecules. So we have hydrogen, we have oxygen, and we have another hydrogen. Okay, oxygen has 6 valence electrons, hydrogen has 1, so we have 8 total. There's 2, 4, 6, 8. I'm sorry. Anybody else super stopped up today? I know I am. I don't know why the allergies are not subsiding yet. Okay. H2O, 2 H2Os, 1, 2. All right, and then lastly, we have 4 CO2 molecules. So we have carbon, we have 2 oxygens, 1 on each side. Carbon has 4 valence electrons, oxygen has 6, so that's 12, 13, 14, 15, 16 total. So there's 2, 4, 6, 8, 10, 12, 14, 16, because carbon needs its 8. Okay, now again, just like I did with the O2 molecules, I'm just going to draw the bonded pairs just to save time here, because that's all we're really going to look at anyway is the bonds. This way we can count them. Ooh. Sorry, this is hard to do on the laptop. Doing my best. Okay, 4 of these. 1, 2, 3, 4. Okay. All right, so now lastly, step 4, we are going to look at our table here, our table on page, let's see, 456, and that's going to have all of our bond energies listed for us there. So number 4, let's look at that. We'll go ahead and list them out. So let's do an H single bond to carbon. That bond energy is let's see, 411. Our next one, so we've got carbon and hydrogen bonded. We've got a triple bond between two carbons. So let's look at that. So carbon, I'm just gonna put carbon, 3 carbon. That's the best way I know how to do it because I can't do triple on here. And that's gonna be 835. Takes a lot of energy to break that bond. This is just carbon to hydrogen again, the same thing, just flip-flopped. Then I've got a double bond between 2 oxygens. So oxygen double bonded, whoop, oxygen double bonded to oxygen. That one's gonna equal 494. Whoop, I don't know why I did an extra 9 there. Okay, now I have a single bond between hydrogen and oxygen. So hydrogen to oxygen. 459. Okay, we've also got a double bond here between a carbon and an oxygen. So carbon double bonded to oxygen, and that's going to be 799. Okay, so I found all of my, just trying to make this smaller. I found all of my values here. Now I just need to plug it in the equation. So the equation I'm using is equation 13.2. So it's going to be all of the energy required to break the bonds. So all of the energy on this side of the equation, and you see here is my divider, minus all of the energy released when the bonds form. So all of the energy on this side minus all of the energy on this side. So we're going to go ahead and plug that in, and that's going to be change in enthalpy is equal to, so let's do it in parentheses, okay? So we've got carbon and hydrogen here, and we're going to count how many of those we have. So we have 1, 2, 3, 4. So 4 moles times carbon to hydrogen is 411, and that was kilojoules per mole. Okay, plus we've got carbon triple bonded to carbon, and we've got 2 of those. So 2 moles and that's 835 kilojoules per mole, plus oxygen double bonded to oxygen, double bonded to oxygen, 494, and there's 1, 2, 3, 4, 5 of those. So 5 moles times 494 kilojoules per mole. And I'm sorry that it's doing it this way. I'll try to fix it for you in 1 second. Okay, and that is all we have, all the energy we have on the left side of our equation here. Okay, so I just want to make sure I'm doing this right before I get too far. All right, so let me fix this so you can kind of see. I'm going to spread this out a little bit, so hopefully it'll go in one line. Let's see if we can get it to do that. Not quite. Close enough, though. Okay, so here, I'm just going to add a bracket. Whoops. Oh, goodness. This thing is so finicky. I'm just going to add a bracket. Hopefully you can see that. Starting around the 4. And I'm also going to add a bracket here behind this moles right here. Let me just move that for you. Okay, there we go. All right, so this whole thing added up together, and then it's going to be all of that minus, I'm sorry, this is crazy. Okay, minus, now I'm going to start another big bracket, okay, because it's going to be all of this energy added together. Okay, so we've got hydrogen bonded to oxygen. Let's count how many we have. 1, 2, 3, 4. So 4 moles whoops. We're supposed to have a bracket here, aren't we? We're supposed to have minus and a bracket. Okay, so 4 moles. Oh my goodness, y'all, I'm sorry. Okay, moles times hydrogen to oxygen was 459 kilojoules per mole. Okay, and we're gonna add that to, we have carbon double bonded to oxygen here, and we have that 1, 2, 3, 4, 5, 6, 7, 8 times. So 8 moles times, and that was 799 kilojoules per mole. I'm going to close that parentheses, and I'm going to close the bracket because that's the end of my product side. Okay, so let's just make sure we did that right. I'm just double checking myself. Okay, looks good. Now let's kind of stretch this out so that it looks a little nicer. Okay, so in your calculator, you have, let me get my calculator out. Might need that today. In your calculator, you will have parentheses, another parentheses, 4 times 411, close your parentheses, plus, open parentheses, 2 times 835, close parentheses, plus, open parentheses, 5 times 494, close parentheses, minus, open parentheses, 4 times 459, close parentheses, plus, open parentheses, 8 times 799, close parentheses, Okay, and I got negative 2,444. So let's see. Write it right here. Equals negative 2,444. All the moles are going to cancel because we've got mole over mole, so the answer will be in kilojoules. And that is the change in enthalpy for our reaction. And because it's negative, this is an exothermic reaction. Okay? And they didn't ask you that, but that way you know. Okay, so that's 13.3 from the Lewis structures. The rest of it was on yesterday's instruction. If you need further help with that, how we got the equation, that's all you missed. So let me clear this out, and we're going to talk a little bit about a new subject, and then we'll do some more practice problems. And maybe someone will come to class, maybe not. Maybe I'll just be here by myself talking to a screen. All right, either way, it's fine. Hopefully you'll watch it later. Okay, so I'm going to start on page 460, and we're going to start towards the bottom where it says in purple, Hess's Law. And this is going to be a weird discussion, so hopefully you understand. It might be a little difficult, but don't worry. Just try to pick up as much as you can, and at the end of the section, we'll kind of summarize what you have to know for this class. Okay, so far we did say there were 3 ways we can calculate change in enthalpy from a chemical reaction. Number 1 way was experimental, and that was the extra credit experiment I sent you a link for on Homeschoolminder that you can watch and do the report for if you're interested. But yes, you can experimentally figure out a change in enthalpy for a reaction. Secondly, we can use Lewis structures like we just did. I personally don't like that method. It's just time consuming to me. So the third method is, to me, the best method, and it makes use of a law called Hess's Law. Hess's Law is named after a named after Germain Henry Hess, a famous Russian chemist whose experimental work led to its development. And Hess's Law says that enthalpy is a state function. A state function is any quantity that depends on the final destination, not the way we get to the destination. So enthalpy, as we said, is a change in energy in a chemical reaction, right? I'll make sure I quoted that right to you. That was at the very beginning of this module. The energy change that accompanies a chemical reaction. So enthalpy is a state function. That means that this is a quantity that depends solely on the final destination, not on how we get there. So let me explain. I'm just going to read you a little scenario that's at the top of 461. It says, for example, Busch Gardens is an amusement park in Williamsburg, Virginia. People from all over the mid-Atlantic United States come to this park for a fun-filled day of rides, shows, and other attractions. Two people can leave from the same city and take completely different routes to the park. One of them may take a route that is made up mostly of highways. Most likely, he will have to travel a little out of the way to stay on the highway, but since highway travel is faster, he might end up saving time. On the other hand, if someone wants to take the straightest route to Busch Gardens, he will have to travel the back roads. One person might travel the highway route and the other might travel the back roads. In the end, they will both get to Busch Gardens and have the same amount of fun. In this case, fun could be described as a state function. Regardless of the route that each person took, they both got to the same location, which was Busch Gardens, and therefore had the same amount of fun once they arrived. So in this scenario, fun is a state function, just like we said enthalpy is, but many other things are not. So here's some things that are not state functions in this scenario. The number of miles traveled, because one person traveled on the highway and one person traveled back roads, so the mileage is going to be different. Time is not a state function because one person's travel is probably going to be longer than another. So some of the quantities associated with the trip depend on the path taken. So those are not state functions. The distance and the time all depends on what path you take. It's not going to be the same if you take a different path, okay? However, the quantity of how much fun you'll have is not dependent on the route you take. You're going to have fun regardless of how you get there, if that makes sense. Okay, so Hess's law, like I said, this is going to be weird, so just grasp what you can and we'll kind of summarize it at the end. So don't worry too much if you don't understand. Hess's law tells us that enthalpy is also a state function. So in other words, the amount of energy contained in a substance is independent of how it's made. For example, they give you two equations on page 461 towards the middle, and those are two different equations for how to make water. As you can see, we have two totally different methods. We have two reactants and one product in the first equation. The second equation has one reactant and two products. So the enthalpy of that water, it's going to be the same in the first equation as the enthalpy of the water in the second equation, even though we used two different ways of making the water. So these different chemical equations represent two different paths of how to make water, right? But regardless of which equation we use, the enthalpy is going to be exactly the same. And that's what Hess's law is telling us. It's saying that no matter how you get to this substance, it's going to have the same enthalpy. Okay, so if we somehow knew the enthalpy of each substance in a chemical equation, we could simply take the difference of the enthalpies of the products and the enthalpies of the reactants to get the change in enthalpy of the reaction, which would be change in H. Hess's law tells us that the enthalpy of a given substance is independent of the way it was made. So it doesn't matter how you make it, it's going to be the same. This is a standard way of measuring the enthalpy of substances. So we can use that information to calculate the change in enthalpy of any reaction that contains the substances that we know these values for, regardless of how they were made for that particular chemical equation. It's really hard to measure the enthalpy of an individual substance, which is what we need to use Hess's law. But this conversation was not in vain, because there is one way, and it's called the enthalpy of formation. That word formation should sound familiar to you. We talked about it a couple modules back when we talked about different types of chemical reactions that we could predict. Formation reaction, as you know, starts with elements and ends with one substance. Okay, so the enthalpy of formation, which is symbolized with a delta, a triangle, H, and a subscript of F for formation. This is the enthalpy of formation, a change in enthalpy of a formation reaction. So that reaction I just talked to you about, that kind of reaction. So let's see. The enthalpy of formation of any given substance is just the change in enthalpy of the formation reaction that creates the substance. So all we have to do is run the formation reaction in a calorimeter, find the enthalpy of the formation. And you might be confused as to how this helps us in any way. Well, the enthalpy of any element in its elemental form, so its smallest form it can go to, so oxygen, O2, hydrogen, H2, carbon, in its most elemental form, the enthalpy is equal to 0. So if we use elements in their elemental form for the reactants of the chemical equation, and then or the chemical reaction, and then you create a formation reaction, then there's only one product left over when you have a formation reaction, right? So the change in enthalpy of the formation equation is going to be, in essence, the enthalpy of that substance, because you have 0 on the reactant side because they're all elements. So it's going to be 0 plus 0 plus 0 on the reactant side. So whatever you get on the product side for that one substance that we're creating, that's going to be the enthalpy of that substance. So it's kind of interesting, kind of cool, I think, because I'm a nerd. But you'll kind of see how this works in just a minute. So if we had a table of all these change in enthalpy, these enthalpy of formations, then we could calculate the change in enthalpy of any reaction that uses these substances. Lucky for you, your book does have one. All right, so before we talk about the table, we're going to talk about some terminology. The change in enthalpy of a chemical reaction can change depending on the conditions under which the reaction occurs. So before we kind of talked about standard temperature and pressure last module. Well, this module we're going to talk about standard conditions. So most chemistry is done at room temperature, which is 25 degrees Celsius, and normal atmospheric pressure, which is 1 atmosphere. You should know that. And this is called standard conditions. This is not the same as standard temperature and pressure. Standard temperature and pressure is different because that's at 0 degrees Celsius. We're talking standard conditions. That's 25 degrees Celsius and 1 atmosphere pressure. Okay. All right. So let's see. In the table 13.3 on page 462 at the bottom, that is going to give you the standard enthalpies of formations for a lot of common substances that we're going to use. So let's see. To indicate that they're under standard conditions, like we just talked about, there's a degree symbol. So we call them standard enthalpies of formation. And when you see that little degree symbol, that's going to indicate that the formation was measured at standard conditions at 25 degrees Celsius and 1 atmosphere. So when you see this right here, change in enthalpy, formation, and a degree symbol. That's what that's going to look like. And you'll see that in the second column in blue on page 452 there. All right, I just wanted to kind of explain what you're going to see. So there's a lot of common substances. You see the numeric value there beside them. Another thing you should notice is that they can be either positive or negative. Some formation reactions are exothermic while some are endothermic. So notice that the enthalpy of formation depends also on the state of the substance. So if you notice, just look at the first one, H2O, you'll see that there's a G in parentheses, which means it's in its gaseous phase. This is the standard enthalpy of formation for water in gas form only. If it was an equation and they gave you solid form of water, then you could not use that value or this table because that's not listed here at all. So pay attention to the state: gas, liquid, solid, AQ, aqueous. Pay attention to those symbols because it has to match up with your table. So just pay close attention there. And it makes sense that we need to know that because it takes more energy to turn water from a liquid to a gas. So it makes sense that your change in enthalpy is going to have to be greater because it takes more energy to go from phase to phase, right? Okay, so it says the heat released by a reaction that makes gaseous water would be less than the heat released by a reaction that makes liquid water, because the first reaction would have to use some extra energy to make it a gas. Whereas just going to a liquid, it's going to have some more heat to release because it didn't use as much of that energy. So that's explaining to you the difference in the numbers there. Just something to keep in mind. Always look at the face. Okay, and I do want to point out equation 13.3. That's kind of 1/3 of the way down on page 463. And that's just giving you a new equation. Pretty much should be familiar by now. The change in enthalpy under standard conditions, right, is equal to, you'll see a funky looking E symbol, and that means the summation. So all of that added up together. So the summation of the standard enthalpies of formation of your products, so all the energies for your products added up together, minus, again, the summation of all of the standard enthalpies for your reactants. So all of the energy on the product side minus all of the energy on the reactant side, okay? We'll do some practice with this. But just something to keep in mind, a negative change in enthalpy will indicate an exothermic reaction, and a positive change in enthalpy will still indicate an endothermic reaction. So just like we said before, negative value exothermic, positive value endothermic. Okay, and let's see, we have to make sure that the equation tells us that it's taking place in standard conditions. And if they say that it did not take place under standard conditions, that's when we'd have to go back and use the Lewis structures. So now we're going to kind of summarize what you need to know because that was a lot. So you need to know the definition of Hess's law, which is that enthalpy is a state function. You need to know what a state function is. That's a value that is independent of the path that you take to get there. So a value, let me actually read you the exact definition just as a refresher. Any quantity that depends solely on the final destination, not on the way we get to that destination. Okay, so you need to know those two things. You need to know the definition of enthalpy of formation, and that is the change in enthalpy of a formation reaction. And you need to know equation 13.3, which we just talked about, which should kind of be easy. You also need to know that the standard enthalpy of formation for an element, so a basic, like you're looking at the periodic table here, any elements, the standard enthalpy of formation for any of those is just going to be 0. That should be easy to remember. Okay, same for homonuclear diatomics. So hydrogen H2 or oxygen O2, those are going to be equal to 0 as well. Even though it has a 2 subscript, that's its most elemental form. So that's going to be equal to 0 too. All right, so we're going to do example 13.3, and I may or may not have time to do that on your own questions. So if not, I'll probably assign that for homework. So let's do example 13.3 first. It's asking us what the change in enthalpy is of the following reaction, and it gives us a reaction there at the bottom. If you turn the page, it's also asking, is it exothermic or endothermic? Okay, so we're going to look at table 13.3 to see, okay, we have all of the standard enthalpies of formation for all the substances in our equation except for O2. Well, luckily we know that O2's standard enthalpy, of formation is just going to be 0. Okay, so let's see. Now we need to make sure when we're looking for the standard enthalpy of formation that we're looking at the substance and the phase. So we got to make sure that the phases are matching up. And let's see. Okay, so also, if we were working with O2 in liquid form instead of O2 in gas form, we could not solve the problem because we're working under standard conditions, and under standard conditions, oxygen is a gas, not a liquid. It's just something to keep in mind. Okay, so if you'll see there, they put the change in enthalpy, and they're just going to calculate it from the table. So they're looking at the equation, and remember we do the products added up together first. So we're looking at the product. Well, there's only one product, NO2, and it's in gas form, and there's 2 moles of NO2. So that's why they have 2 moles times, and then they got their value from the table, which was 33.2 kilojoules per mole, minus, and now they're going to add up all their reactant sides. So we have NO in gas form, and that is 90.3, and there's 2 moles of that, so that's why they have 2 moles times 90.3 kilojoules over mole, plus, and then we have 1 mole of O2, which is just 0. You could really skip that step because you're just adding 0, but you can write it for practice if you want. So then they're going to do all that in the calculator. They get negative 114.2 kilojoules. And because it's negative, we have an exothermic reaction. Okay, one more example. Some gasoline companies put a small amount of liquid ethyl alcohol into their gasoline. What is the standard change in enthalpy for the complete combustion of this chemical? So they don't give us an equation this time, so we have to come up with it ourselves. Complete combustion just means we take our substance they gave us plus O2, and that's going to make carbon dioxide and water. So they give you the equation there about 3/4 of the way down on page 464. Now, and they've balanced it for you. And so they also added the phases. So don't forget that part if you have to write an equation to include the phase for each substance so that you know if you can use that table. Okay, so they included the phases, and now they're going to look for all the values on the table, and they're all there. So now they're just going to do the same equation. So the same equation, make sure we look at the coefficients to multiply. So we're going to start with the products, don't forget. So we've got 2 moles of carbon dioxide. So 2 times negative 394 kilojoules per mole, plus we have another product, 3 moles. So 3 moles times negative 242, that's the value for H2O. And then all of that added together, minus, and then we're going to add all of the reactants together. So let's start with the C2H6O. There's only 1 mole of that. And they've got that times negative 278, plus our second reactant is O2, and there's 3 moles of that, and again, that's just 0, so you can leave it out if you want to, or include it, up to you. But once you put it in the calculator, you get negative 1,236 kilojoules, and that would be your answer. I think I have time to do one, so I'm going to go ahead and do that now. All right, so this is 13.4 on your own questions. Apologize. Okay, 13.4. When you use a pocket cigarette lighter, hopefully not to light cigarettes, thank you, you are burning gaseous butane, C4H10. Assuming it is complete combustion, what is the standard change in enthalpy for this reaction? Do not use bond energies to solve this problem. Use Hess's law. So they're telling us don't do the Lewis structures, use Hess's law. Okay, so step 1, I need an equation. Always, always. So step 1, equation. Okay. All right, they give us our substance, which is C4H10. Okay, and this, they tell me is, let me take this down so that looks better. They tell me this is a complete combustion reaction, so I'm adding it to O2. That's technically an arrow, you guys should know that. And that's going to produce water and carbon dioxide. Okay, now I need to balance it. This is going to get tricky, but we can do it. So first of all, I have 4 carbons here. I'm gonna need 4 carbons on this side. So I'm gonna go ahead and add a 4 right there. Okay, now I have 4 and 4, but this affected my oxygens. So here I have 8, 9 oxygens. Here I have 2. Ooh, I'm not gonna start there because that's awkward. Okay, so I have 10 hydrogens. Let's try hydrogens. And here I have 2. So let's put a 5 right here and make that 10. Okay, so now I have 5 plus 8. I have 13 oxygens and 2 oxygens on this side. So we're gonna have to do a fraction. So 13 divided by 2 oxygens. Oh, no, no, no. Oh no. Okay, come back. Okay, sorry, I was just trying to make it look better for you guys, but it's not gonna work. Oh dear. Okay, we're balancing here. So let me just go to step 2, balancing. And we'll keep going. I messed it up. Okay, 13 divided by 2, and that's O2 molecules. And that's gonna produce 5 H2O plus 4 CO2. Okay, so we're having to multiply this by a fraction to get 13 oxygens on this side. Now I have to multiply the whole thing by 2 to get this 2 on the denominator to cancel. And I need to multiply this whole side by 2 because I have to do the same thing on this side. Okay, so let's factor it out. So 2 times this is going to be 2 of these. I'm going to go ahead and take this 2 out. I hope this isn't too confusing doing it on the computer like this. Okay, and then if I multiply that 2 that was out there by this 13 over 2, I'm just going to get 13. Okay, let's factor this out. 2 times 5 is going to make 10. And then 2 times 4 is going to make 8. Okay, so let's make sure this is our balanced chemical equation. Take that out. Okay, and we do need to add the phases real quick. So they tell me that this is gaseous butane. We know that oxygen in its elemental form is gaseous. Okay, we know that water is gaseous, and we know that carbon dioxide is gaseous. So these are all gases. Okay, now that we have balanced it and written our phases, we are ready to roll. So there's our equation, our balanced equation. Step 2, we're just going to use our equation that we just talked about earlier. Okay, so change in enthalpy standard. There should be a degree symbol, but I can't do that on here right now. Is going to be equal to, I'm going to put a bracket because we're going to sum up all of our products first. Okay, so the products, we've got 10 H2O, so 10 moles times, I'm going to look at the table 13.3 at the bottom of page 462, and I've got negative 242 kilojoules per mole. There needs to be another parentheses there. I'm adding up all of the products. So there's one product. Now I've got this product. So let's do 8 moles, because there's a coefficient of 8, times CO2 gas, negative 394 kilojoules per mole. Close that parentheses. That's all of my products. So I'm going to close that bracket. That whole thing minus, open a new bracket, all of my reactants. So I have 2 moles here of butane. So 2 moles times, and that's on the right side of the table, negative 126 kilojoules per mole. Plus, we got to add it to our other reactant, 13 moles. And then we know O2 is just 0 because it's in its elemental form, okay? So now I have everything written out, and I'm just going to plug it in the calculator. I'm going to walk you through how to plug it in. Hopefully you're following along. Okay, open parentheses, 10 times negative 242, close parentheses, plus, open parentheses, 8 times negative 394, close parentheses, minus, open, 2 times negative 126. I'm just going to close because 13 times 0 is just 0. So it's this number plus 0, which is just going to be that number. So I'm not even going to include that part. I get negative 5,320 kilojoules. And that's going to be your answer. Negative 5,320 kilojoules. Notice it's negative, so that means this was an exothermic reaction, which should make sense because any combustion reaction is going to produce heat. So makes sense. All right, it hasn't cut me off of this meeting yet, so I guess it gave me extra time. So I'm going to go ahead and do 13.5 for you so you don't have to do it for homework. Hopefully you will go back and watch this so that it will be helpful to you. I'm going to go ahead and clear this out. This is 13.5 on your own. Okay, let's read what it says. To make the shells that house and protect them, many shellfish take solid lime, CaO, from the ocean floor and react it with gaseous carbon dioxide that has been exhaled by marine organisms. The resulting calcium carbonate is the major component of their shell. What is the standard change in enthalpy for this reaction? Okay, so number one, I definitely need an equation. We always know that. Okay, so they tell me the first reactant is the solid lime, the CaO. So I know I have CaO in solid form plus, and they tell me they're using gaseous carbon dioxide that the marine organisms are exhaling. So I have CO2 in gas form. And I'm producing, that should be an arrow, you guys know that. They tell me the result is calcium carbonate. So CaCO3. Now I know calcium has a charge of 2, and luckily carbonate has a charge of -2. So because they're the same number, I don't need any subscripts. It's just going to stay just like that. All right, now let's see if it's balanced. I have 1 calcium here, 1 calcium here. I have 3 oxygens here, 3 oxygens here, 1 carbon here, and 1 carbon here. All right, we're already balanced. Perfect. So this is an easy one. All right, so now I'm just going to use my equation. So change in enthalpy standard, should be a degree symbol there, is going to equal the sum of the energies of the products minus the sum of the energies of the reactants. So let's start with our product, which is CaCO3. Oh, I'm sorry, I forgot to include that this is going to be in solid form because it's their shell. All right, so let's look at the table and see if we can find the value for CaCO3 in solid form. Luckily, it is there. I have 1 mole, so if you want to include this, you can. There's only 1 product, so I don't really need a set of brackets. 1 mole times, I lost it. Okay, -1207 kilojoules per mole. Okay, that's my only product, so I'm done with the product side. So minus, now I'm gonna do a bracket since there's 2 of them with my reactant side. So CaO in the solid form, 1 mole of it. And it looks like -635 plus my other reactant, which is CO2 gas. That's -394, and there's 1 mole of those. I'm gonna close the bracket. All right, in your calculator. Notice here we're multiplying every one by 1. So 1 times this, 1 times this, 1 times this, because we don't have any other coefficients. So really, if you guys want to, skip the step of the multiplying everything by 1 because that's pointless because it's going to be the same thing. I'm just going to plug it in the calculator this way. -1207 minus parentheses negative 635 plus negative 394. Close my parentheses. And I get negative 178 kilojoules of energy was released. So this is exothermic because it's negative. Okay, I hope all that made sense. If you have any questions, since no one was here today, please feel free to reach out to me or, watch the video first, obviously. I will place your homework on Homeschool Minder, and I hope everyone has a great weekend. We have 3 weeks of school left. We're doing awesome. So hang in there and let me know if you need help with anything this weekend. Bye, guys.